Hey there. So next we're moving into section 6.4 where we look at a very interesting technique for finding derivatives of crazier looking functions. It's going to seem like a little bit of a loophole, so I think it's very interesting and I'm excited to get started. So here we go. All right, section 6.4, implicit differentiation. So before we get to the calculus aspect of it, we do need to talk a moment about explicit versus implicit. Okay, so in almost all examples and applications that we've done so far in this class, we've seen functions defined in the form y equals f of x, where y is given explicitly in terms of x, or as an explicit function of x. And all that really means is that we can write the function with y by itself, such as this expression here, like y equals. And then over here, all you have is an expression dealing with the other variable. Okay? Now, if we look at a different type of equation like this one is not given explicitly in terms of x, 3xy minus 4x equals 8, but we can express this as an explicit function of x by solving for y. Not too big of an issue here if we just take this equation here, try to get y by itself, we would add 4x to both sides, and then divide both sides by 3x. And then now we've got y explicitly in terms of x. Y equals by itself, no other y's over on this side, okay? Only the other variable, okay? However, some equations in x and y cannot easily be solved for y, and some equations cannot be solved for y at all. So for example, we can solve the equation for y right here, this one. We can technically solve for y in this equation, y squared plus 3xy plus 4x squared equals 0, using the quadratic formula. It would be a mess, it would be crazy, but we could technically do it. Okay, but an equation such as this one, y to the 5th power with a bunch of different powers of x's and y's all scattered throughout equal to 0, that can't be solved for y at all. Okay, so sometimes it's not even possible, and sometimes it's just really unreasonable to even try. Okay, these previous two equations are example of y being given implicitly in terms of x, where we do not have y by itself. Maybe you could get y by itself, or maybe you can't, but if you've got x's and y's kind of all scattered around, then that means that you've got y being given implicit. Okay, so that's the difference. Implicit is you've got y kind of all scattered around, and explicit means that you have y by itself. All right? Okay, so moving on to the technique of implicit differentiation. So when y is given implicitly in terms of x, so you've got an equation like this where y is scattered all over the place, it may still be possible to find the derivative dy dx by a process called implicit differentiation. So in doing so, we assume that there exists some function or functions f, which we may or may not be able to find, such that y equals f of x and dy dx exists. We take the derivative of both sides of the equation. And it gets a little bit strange, but it is kind of cool that we can find dy dx without having to have y equals by itself. So keep in mind that we're going to use the notation dy dx with implicit differentiation to make it clear which variable is independent. So in this case, the x would be the independent variable, and then this indicates that the dependent variable is the y. And then this is particularly important once we start doing applications in the next section, where the variables might be other letters. We might be doing all kinds of different shapes and letters and stuff, and so you might not just have x and y involved. So a very important thing to keep in mind when performing implicit differentiation is the chain rule. Okay, this is usually where all of the mistakes come from when doing implicit differentiation. Whenever we take the derivative of a variable, which itself is assumed to be a function of another variable. So all through this, we're assuming that any y's that are showing up are functions of x. Okay, so that's the important thing to keep in mind. When we're taking the derivative of a variable, when we're assuming that that variable is a function of x or a function of a different variable, okay, with respect to some other variable, okay, and I know that's getting a little bit messy, but that's because we might be having all kinds of different letters involved once we start doing applications, okay, but we must apply the chain rule. And just a quick little example of what I mean by that, if we're going to do the derivative of y cubed, and we're assuming that y itself is a function of x, And this notation here, d over dx, this means take the derivative with respect to x, and we're assuming that y is a function of x. You have to do the chain rule. So you imagine that inside that y is a big expression in x, but we don't know what it is. Well, so the chain rule would say that you just do the power rule on the outside, so bring the power down and reduce the power by 1, but then the chain rule says you have to multiply by the derivative of the inside, so dy dx. Okay, so this is going to show up all the time when we're taking the derivative implicitly. When you take the derivative with respect to x of any x type expressions, you'll just take the derivative how you normally would. But when you're taking the derivative with respect to x of any of the y's, we do have to consider this chain rule because we're assuming that y is a function of x. Okay, so in that way, you can probably tell that this does seem like a little bit of a loophole. Okay, so let's try an example here. Let's find dy dx if 3xy plus 4y squared equals 10. So again, I don't want to solve for y. I want to just dive right in and take the derivative of both sides of the equation implicitly. Okay, and specifically, pay attention to the notation here. Dy dx means that we're taking the derivative of a function y with respect to x. So I'm going to write this out in several different steps for this first example so that we can really get used to this. Okay, so the way I want to write this is I'm going to write it as d over dx times the left-hand side. So there's the 3xy plus 4y squared. Okay, equals, and we're going to go the derivative with respect to x on the right-hand side. Okay, so we're taking the derivative on both sides with respect to x. Okay, now what we're going to do is we're going to take the derivative of each piece in there, and the way we need to think about this is any of the y's, there's going to be chain rule involved because we're assuming that y is a function of x. And then when we see this part right here specifically, that's a product rule because we have 3x times some other function in x. So that's a product rule, and that's a little bit of a thing that's kind of tricky that can throw people off. Okay, so here we go. We're going to have to go, I'll break it down in a couple more steps. D over dx of the 3xy plus the d over dx of the 4y squared. And then on the right-hand side, if I want to just start cleaning this up, the derivative of a constant, that's just 0. So that's nice. Okay, so yeah, I wanted to mention that right here, this is going to be a product rule. Let's make a note of that. That's a product rule because it's like x times a function in x. So there's a product there. Okay, so here we go. The derivative of this, I'm going to pretty much consider the 3x and the y as separate pieces. Okay, so product rule, we got to go first times the derivative of the second, okay? And so the derivative of y with respect to x, that's dy dx. Okay, anytime we're taking the derivative of y, we have to make sure that we write it as dy dx. Taking the derivative of any of the x terms, just do it normally, but any of the y terms, there's going to be this dy dx that pops out. Okay, a little bit weird, but this is what I'm saying. It's almost like a little bit of a loophole where we're going to find dy dx without ever having to solve this equation for y. Okay, so continuing, that's first times the derivative of the second plus the second, which is just y, times the derivative of the first. So the derivative of 3x is just 3. Because remember, we're taking the derivative with respect to x. So that one is just normal derivative. Okay, so that's the product rule. Now we go plus, and now the derivative of 4y squared. Okay, so like I said, this y is like a function of x. So there's a chain rule involved. So we're going to use the power rule on the outer part. So the 2 multiplies down with the 4, and we get 8y, reduce the power by 1, and then times the derivative of y with respect to x. Okay, so there's the chain rule again. Okay. Takes some getting used to, but as we do more examples, you'll get the hang of that. Whenever we have the derivative of the y part, a dy dx pops out from the chain rule. okay? So now what we want to do is the whole point is we're trying to find dy dx. And now notice that we've got dy dx that's kind of scattered around throughout this equation a little bit. So what we want to do is we want to just solve this for dy dx. Pretend that dy dx is just a variable that you're trying to solve for. Okay, so the idea is I want to see wherever all of the dy dx terms show up, I want to keep those all on one side of the equal sign. And I want to get anything that does not have a dy dx in it to the other side of the equal sign. And this will be a common technique. So looking at this first part, the 3x dy dx, I want to keep that on the left-hand side. This 8y, and that y to the first power, I want to erase that little first power because it kind of looks like y prime. This is just y to the first power right there. Okay, let me just, okay. And then times dy dx. So that term also needs to stay on the left-hand side. So what I want to do, let me just, maybe I'll rewrite this as 3x dy dx, kind of get rid of all the parentheses stuff. Plus, I prefer to write this like 3y, and then plus 8y dy dx. Okay, so what I want to do is I want to keep anything with a dy dx in it on one side and move anything that doesn't have a dy dx in it to the other side. So let's subtract this 3y from both sides. And then I'll continue the work over here. So now we've got 3x dy dx plus 8y dy dx equals negative 3y. And so the point of doing that is now, since everything on the left-hand side has a dy dx in it, we can factor that out as the GCF. So dy dx can now be factored out, 3x plus 8y. And that's really nice because now we've got dy dx showing up in just one location multiplied with this stuff. So we can divide both sides of the equation by this stuff. And so cancel that. And we've isolated dy dx. Okay, and that is it. We have dy dx. Notice that the result still has y's involved, x's and y's involved, but that's okay because we would start trying to do some analysis where we've got x values and y values, and you can still do all kinds of like slope of the tangent line and all kinds of stuff later on, okay? So our answer typically does have x's and y's involved, but we did manage to find out an expression for dy dx in terms of x and y. And remember, this whole time, we're assuming that y is a function of x. Okay, pretty interesting stuff. Takes a while to get used to, especially the fact that we've got weird little product rules and chain rules showing up all over the place. So I'll make a new video to pick up on example 2.